Hello everyone, my name is Ryan and today we're going to be looking at Lab 3 from Physics 1 called Black Hole. Let's get into it. So there's going to be two parts to this lab. The first part we are given a black hole of an unknown mass, which is going to be located at the origin, and a star orbiting the black hole where we're given a mass for the star, the x and y coordinates with respect to the origin, and an initial velocity. From this information, we're asked to determine the force of the gravity on the star by the black hole, the parallel and perpendicular components of this gravitational force, which will be the net force since it's the only force acting on this object, and then determine ultimately the mass of the black hole is the main point of this first part. Now, part two, we're going to use what we discovered from part one, which is the mass of the black hole, and then we are also going to be given for this part a mass, position, and initial velocity of a planet which is now orbiting the black hole, and a spaceship that we've taken to the surface of this planet. And what we're trying to find out here is what are all the forces acting on the ship and the planet now, because there's three objects in this part of the problem. There's going to be multiple forces of gravity that we have to deal with, and those are going to serve in our calculations of the net force. And then the final part of part two is to determine the initial velocity that we need for the spaceship to leave from the planet, pass close to the black hole, and exit the system without crashing into the planet or getting sucked back into the black hole. The goals of this lab are to use a computer model to do iterative calculations that would not be efficient to do by hand in a loop, to approximate the trajectories of objects due to one or more gravitational forces, and to observe how the parallel and perpendicular components of the net force on an object in orbit change over time, as well as analyze how, by changing the initial velocity of an object, we can drastically change the long-term trajectory of this object as it undergoes a changing net force. The physics concepts we're going to be using in creating our computer model are the momentum principle, the net force parallel and perpendicular equations, and the gravity equation. Now, the net force parallel is equal to the change in the magnitude of the momentum over the change in time, multiplied by the unit vector for momentum. And the net force perpendicular for our purposes is just going to be equal to the net force minus the net force parallel, because those are the only two components of the net force, so we can deduce that. Here you can see our computer model where we've defined the force of gravity, the mass of the star, and our time interval. If we scroll down, we see where we've calculated the momentum initial and momentum final so that we can obtain our net force. And of course, we have our parallel and perpendicular components of the change in momentum. And then finally, our mass of the black hole, which we'll talk about in a little bit more detail, how we obtain that later. And then the arrows which show visually the different components of the net force. And if we run this, you can see that over time, these arrows, like the pink one showing here, the parallel component of the momentum is changing over time, and of course the perpendicular arrow as well, this blue one. Another aspect of this code is that it outputs an approximation of the black hole mass with each iteration, and we use the average of these values in order to come up with a mass to use in the next part of our lab for the black hole. And once we've done that, we then calculate the net forces that are acting on both the planet and the ship. And from there, we're able to guess and check to find the initial velocity that we need in order to go near the black hole. So be able to take off from the planet and go around the black hole, but not to enter the orbit of the black hole. So here are the results that we got from the two parts of the lab. The black hole mass obtained here, of course, which we use the momentum principle and the law of universal gravitation in our model. This equation may look a little bit different, but we basically just moved everything from one side of the equation in order to obtain one of the masses, which we were missing, the black hole mass. And then we use the guess and check strategy in order to find the initial velocity which we needed, which is this vector. So we might ask, how are the parallel and perpendicular components of momentum different from the rate of change of these components? And the answer is, regardless of which direction the parallel and perpendicular components of momentum are pointing in, the rate of change of the components will always be in the same direction as the net force on the object on the axes of those respective components. Now, for example, this means that if the Fnet parallel is in the opposite direction of the current momentum parallel, the rate of change of the parallel component of the momentum will be going against the parallel component of the momentum. Now let's say for the second part of this lab that instead of having the rocket ship shoot out of the system, we wanted it to stay in orbit of the black hole. This would require a different initial velocity from the ship, and this is what I discovered it to be. And I noted that generally you want to start with a wider angle in relation to the black hole and at a lower speed. If you can remember what it looked like the first time through, the pink trajectory just kind of shot right around, narrowly avoiding the black hole off into this direction. This trajectory takes a much wider angle and is able to enter that sweet spot where it will keep going around the black hole. So in conclusion, if the angle is too sharp, then your ship will either get sucked into the black hole or require a speed so fast that the force of gravity by the black hole won't be strong enough to keep the ship in the system. That is the end of our conclusions from this lab, so I thank you for listening in, and hope you have a great rest of your semester.